A rigid body is a special type of system or particle in which the distance between any two pair of particles remains the same. Although a rigid body is an idealized concept, but it serves a lot in the modeling of uh, bodies which are not very compressible, or if we want to study the dynamics of a solid substance, then the rigid body model is a good one, although we know that under high pressure this the solid can be compressed a bit, which in which case the rigidness although is violated, but the distance the change in distance is negligible in comparison with the original distance, and the body can still be modeled with a rigid body to a first approximation. As we have mentioned already mentioned that it is a system of particles, but we know that we know the laws or the laws of mechanics which can be applied to a system of particles. All these laws can be applied to the rigid body because it is a special kind of a system of particles. We shall first uh, ascertain the number of degrees of freedom of a rigid body. Uh, so a rigid body is one for which the distance between its ith and jth particle is the same, and it is a constant. This constant changes with the changing I and j for all I and j. If we consider the body comprises of n particles, then for all I and j which are less than equal to n greater than 1. So this relation is valid, and C12 is in general different from C35. This is the definition of a rigid body. Now coming to the degrees of freedom. In general, it is a system, it is an n-particle system. So, if all the particles of the system were free to move, then the degrees of freedom would have been 3n. But for a rigid body, the degrees of freedom decreases drastically because of this constraint, or the constraint of rigidness. Firstly, it may seem that the degrees of freedom is 3n reduced by the number of constant nc2, but as we shall see that this is not a valid logic, because if we consider n particles and take two of them together, then the number of pairs is nc2, but this nc2 number of constraints are not independent. This can be justified as this. Say we have a rigid body having n number of particles. We first choose a particle of the system. The particle is P1. The particle is located at P1 having coordinate x1, y1 and z1, and this is the mass of the particle. Then to specify its position, we need three coordinates x1, y1, z1. We need three independent coordinates. So we need this. Now if we consider as second point mass m2 located at P2, so it will have coordinates x2, y2 and z2. Of these three, x2, y2, z2, all three are not independent because of the fact that C12 is the distance between C12 is the distance between R1, which is this, minus R2. It is a constant. So this condition makes it only 2 out of 3 are independent. The third one is being determined by the condition. So we get 3 degrees of freedom for the first particle chosen and 2 degrees of freedom for the second particle chosen. If we consider another particle which is not collinear, another point P3, its coordinate is x3, y3, z3, and it is the mass position of the mass m3. This was the position of mass m2. So this is the position of mass m3. But on this there are 3 conditions are imposed. This is C13 and this is C23. Because of these 2 constraints, only 1 out of 3 is independent. Only 1 out of 3 is independent, as C13 and C23 are constants. So these 2 constants reduces the degree of freedom of this particle from 3 to 1. So is independent as C12 is constant. So the degree of freedom comes out to be 6. If we consider now any other particle of the rigid body, say particle point P4 having coordinates x4, y4, z4. For a rigid body, all these three quantities are dependent. All of them are dependent. All 3 are dependent, as C14, C24, C34 are constants. So 3 constraints are imposed on the particle P4. So it doesn't have any free or any independent variable. So we can describe a rigid body by 6 degrees of freedom in general. We can look it upon as this. We have a rigid body, so it is a rigid body. This is the center of mass. So as we shall show you afterwards, that if we want to specify the position of the center of mass, say the position of center of mass with respect to some inertial frame is R having coordinates x, y, z. So to denote the central direction or coordinates of center of mass, we need 3 coordinates, the coordinates of center of mass, and the body may undergo a rotation about its center of mass. So there are 3 degrees of freedom to be assigned to the 3 independent directions of rotation about an axis passing through the center of mass. Or we may choose any point within we may choose any axis passing through a fixed point within a rigid body. Moving rigid body, so if we consider any point, say point which may not be the center of mass, say this is the point. So to denote the translational motion of this point, we need three coordinates and the rotation of the rigid body about an axis passing through this point needs three more coordinates. So which justifies physically the requirement of 6 coordinates. We may approach the problem in a other way round. We may first calculate the number of constraints, that is to be independent constant that is imposed on a rigid body. Let us first calculate this. If we, as we have our good idea that a rigid body, number of constraints, number of independent constants of a rigid body. If we choose a rigid body of comprising of n particles, then it has nc2 number of constants, nc2 number of constants that we have, as stated earlier, is not independent of each other. As we see that if we specify the position of three non-collinear points of a rigid body, this rigid body is entirely specified. So, once the three positions of three non-collinear points are specified, then we have n minus 3 C2 number of constants. These are redundant. As for example, in this case, this particle, if we impose three constraints on this, they do not at all require to fix the number of degrees of freedom because it has already been fixed. So the number, if we want to calculate number of independent constants, this number has to be subtracted from this. This is, so we have the number of constant is n minus 2c3, which is half n into n minus 1 from this, and from this it is n minus 3, n minus 4. If we simplify this, we get n square minus n minus n square minus 7n plus 12. So n square cancels, this is minus 6 and half, this is 12 minus 6n, this is 6n, this 6n is plus sign, n minus 12, so this is 3n minus 6. This is the number of independent constants for a rigid body. So degrees of freedom, coming to degrees of freedom is degree of freedom for an in-particle system, it is minus 3n 3n minus 6 is equal to 6. So we can justify the big number of the degrees of freedom of the rigid body by calculating the number of constants. Once again, in calculating number of constants, we put this logic that it may appear that the number of constant is NC2 because this is the number of in pairs. But once we specify the position of three non-collinear points, the rest of the constants are redundant. So if we want to calculate number of independent constant, this number of pairs, we must subtract the number of constant that arises out of n fourth to all other particles of the system. So this has been subtracted to get this number, which gives you the degrees of freedom of a rigid body. So we find that a rigid body has 6 degrees of freedom. So we may call it, it has 6 degrees of freedom. 3 for translational motion, motion of CM, which is the preferable choice, plus 3 for orientation of the rigid body about an axis, passing through CM. As I have already pointed out, the point may not be chosen as CM, but if we choose the point to be CM, we can utilize the speed view properties of center of mass, which sometimes facilitates calculation. If special cases, if one point of a rigid body is fixed, so once it is fixed, the body cannot have any translational motion. So it can have only rotational motion. Then degree of freedom reduces to 3R. If we have a rigid body whose 2 points is fixed, first point, as the first point is fixed, the body cannot have any translational motion, so degrees of freedom is 3. And if we fix another point, so if we have a rigid body whose 2 points A1 and B1, A1 and A2 are fixed, or say better to write it P1 and P2 are fixed, then the body can only execute a rotation about about P1, P2 axis. So if 2 points are fixed, of a rigid body are fixed, of a RB are fixed, degrees of freedom is simply 1. And if we have 3 non-collinear points of a rigid body is fixed, if 3 non-collinear points of a rigid body are fixed, its motion is freezed. It cannot have any motion and degrees of freedom is 0. Now the thing comes how to represent a rigid body. The different coordinate system used to describe rigid body, I am going to do first. The coordinate system used to describe a rigid body. Used to describe a rigid body. Firstly, if we have a rigid body, say this is a rigid body which is executing a motion. So if we want to specify the translational motion of the rigid body, we assume a coordinate system fixed in space or it is fixed in laboratory. So it is a coordinate system S which is an inertial frame. This is an inertial frame, that means the coordinate system is fixed. Inertial frame. We assume that the Newton's laws of motion are valid in S plane. So this is our inertial frame. It is also called the fixed frame or lap frame. Alternative names are fixed frame or lap frame, because it is a frame fixed in laboratory. Obviously, we assume that the laboratory is not moving. And we choose a coordinate system which is firstly parallel to S, and it is an intermediate coordinate system. Say this is S intermediate. S intermediate is a coordinate system which is situated at, which has its origin at the center of mass of the rigid body. It is the center of mass of the rigid body. So it is a frame origin at the CM of the rigid body and having axis, its coordinate axis parallel to those of S. So basically this intermediate frame SI, I for intermediate frame, this SI specifies the motion of center of mass. It is in general a non-inertial frame. In general, a non-inertial frame. Inertial frame. As the rigid body may hang, rotate, acceleration. And to describe the rotation of the body, we choose a coordinate system which has same origin at the C prime and the axes are rotated. If we choose these axes are Y, X, Z, having origin at O, then these two frames have origin at O prime. This was the YI axis, XI axis, ZI axis, and this is Y prime, Z prime, X prime axis. So this, Y prime, Z prime, X prime. So this coordinate system is denoted as prime frame. So this prime frame is called, S prime frame is called body fixed frame, as if this frame originally when O and O prime were coincident, from them we started our time calculation, then SI and S prime were coincident. All three were coincident. Now with the passage of time, the rigid body starts moving. The rotation, the translation of the rigid body can be described best by the intermediate frame SI. But the rigid body may have rotation as well, apart in addition to its translation. So we choose a frame, S prime frame, which is fixed to the body, a rigid body, and it is fixed rigidly to the rigid body, so that as the rigid body moves, the S frame also moves with this, with the rigid body. So S prime frame is called the body fixed frame. It is the body fixed frame. Uh, Later on, we shall see that principal axis coordinate system is a special class of body fixed frame in which facilitates calculation to a great extent. So PSCS or principal axis coordinate system is a special type of body fixed frame. A special type of which type of body fixed frame is principal axis coordinate system that you have already learned in your earlier classes, that the moment of inertia tensor gets diagonalized in the principal axis coordinate system. With this introduction to the body fixed frame and the lab frame, we now going to describe that rotation and translational motion. Before going to this, I would like to construct the transformation relation relating the quantities in S frame to that in S prime frame. So we have a coordinate system S with axis Z, Y, X having origin at O, and we have intermediate frame is this, YI, XI, ZI, these are small, this is small x, with origin at O prime, this is the center of mass, say center of mass, and then we have the body fixed frame. So body fixed frame is this, Y prime, Z prime, X prime. If we consider a point having coordinate point P having coordinate x, y, z in S frame, and its coordinate is x prime, y prime, z prime in S prime frame. So what is the position? This is the position Ri, R, this is the position vector. This position vector is R prime, and this is capital R. So we have introduced OP, position vector of any point with respect to the inertial frame is R. O prime, the position of the center of mass of the rigid body with respect to S prime is R, and O prime P, the position of this point with respect to the center of mass frame is R prime. So we applying the law of vector addition, we see that R is equal to capital R plus R prime. If we write it in component form, then if we write it in component form, what we shall get? X is equal to, the coordinate of this is capital X, capital Y, capital Z, so this is, and from this we get I cap dot I cap prime x prime I cap dot j cap prime y prime plus I cap dot k cap prime z prime. So even that is, we have represented this vector O O prime P once in S prime frame, another one is in Si frame. And if we take the projections of the unit vectors of S1 frame or say S prime frame in the direction of Si frame, which has the axis parallel to the S frame, we get this relation. In general, we write it as x is equal to a11 x prime, a12 y prime, a13 z prime. The subsequent calculation becomes very easy if we introduce this way. X1 is equal to x, x2 is equal to y. So it is y is equal to x2, z is equal to x3. Similarly, x1 prime is equal to x prime, x2 prime is equal to y prime, x3 prime is equal to z prime. If we introduce this notation, then this relation there becomes x1 is equal to capital X1 a1 alpha x alpha prime summed over alpha is equal to 1 to 3. In general, if we write it if we write it xi, it is capital of xi plus this is summation over alpha ai alpha x alpha prime. This is the transformation relation, and the inverse transformation can obviously obtain that. The inverse transformation, which we may write r prime, this is xi prime is equal to minus xi plus summation over beta a x beta. This is the inverse relation. So we have this transformation relation. But the thing is that for a rigid body, this one will be modified and bit. For a rigid body, we generally denote the position of the ith particle. For ith particle, it is Ri, the position vector of the ith particle, when S prime is related to R times Ri prime. So this is the same. R is the same for all the particles of the rigid body. So the transformation relation, in this case, transformation relation, we have to add an extra suffix. So this we do it, this I suffix is for this, and this alpha suffix, this I suffix we replace by alpha. So this is x alpha plus summation over beta a alpha beta xi prime beta. This is the transformation relation. This herein the first suffix used to denote the particle number. First particle mi, the coordinate of ith particle, first particle is r1. So This first suffix designates the number of particles and the second suffix designates the Cartesian components. That is to say, I in this relation, I is less than equal to n greater than 1 and alpha beta, they are less than equal to 3 greater than 1 for a general motion of a rigid body in 3D. Now, with this introduction of lab frame and the body fixed frame, we shall introduce the translational and rotational motion and the general motion of a rigid body in our next lecture.